Hey everybody. Well, I'm thinking that I won't be able to do two cameras because I keep trying and it keeps not working. So for this lecture, we're going to be looking at inverse functions, which is our function section part 2. We're going to review function composition and then define one-to-one functions in the horizontal line test. Look at what inverse functions are and the test for inverses, and then finding inverse functions graphically and algebraically. So as you may remember, composition is this little circle. It's not a dot, and it does not mean multiplication. It's a circle. And we read this f composed with g of x. So it's this is read f composed with g. When you get to this parenthesis here around the x, you say of, and then x. Composition is defined by this relationship right here. So every time you have a composition, I want to see this next step. So f composed with g of x is equal to, or defined as, f of g of x. We read this f of, every time we get to an open parentheses, we say of g of x. That means we're essentially plugging the function g of x in for all the x's in f's formula. So let's look at this in an example. Here we've got f of x is negative 3x plus 1, and g of x is 5 over x minus 4. Let's first find f composed with g of x. So I'm going to write down f composed with g of x. And again, this next step is very important. I really want to see this written. This means f of g of x. Well, g of x is this fraction, 5 over x minus 4. So this is f of 5 over x minus 4. And now let's write down the formula that we have for f. We have f of x is negative 3x plus 1. So let's see. Negative 3x plus 1. But instead of x, we're going to put 5 over x minus 4. So now we've got, I'm going to write this negative 3 as negative 3 over 1 so that I can more easily multiply. In the numerator, I have negative 15x, negative 15, and in the denominator, x minus 4. And then, again, because I've got a fraction in the first term, I'm going to write the second term as a fraction. And I want to add these, so I'm going to find the least common denominator. Well, my only denominator that isn't 1 is x minus 4, so I'm going to multiply this by x minus 4 over x minus 4. The first fraction stays negative 15 over x minus 4. The second fraction becomes x minus 4 over x minus 4. Now we can combine these into one fraction because they have the same denominator. So we have x minus 4 is the denominator, negative 15 plus x minus 4. And negative 15 minus 4 is negative 19. And this is all divided by x minus 4. It's important to note at the very end, whenever there's an x that will make this thing undefined, what that x is. I noticed that x minus 4 equaling 0 is not okay. We don't want x minus 4 to be 0 because we don't want the denominator of a fraction to be 0. So if I add 4 to both sides, I get that x should not be 4. And that's the value we want to exclude. So I'm just going to put x cannot equal 4. And now let's find g composed with f of x. G composed with f of x. This is defined to be g of f of x. Well, f of x is negative 3x plus 1. So I'm just going to write down what f of x is. Negative 3x plus 1. And now let's write the function for g. G's formula is 5 over x minus 4. And again, instead of putting x here, I'm going to put everything that is in these parentheses. So negative 3x plus 1. In the numerator I have 5. Then I have negative 3x. Positive 1 minus 4 is negative 3. And to make this easier to read, I'm going to factor out a negative 3. And like we've talked about in class, negative in the denominator makes it harder to understand the fraction or to use the fraction later. So I'm going to move this fraction out front. I've got 5 over 3 times x plus 1. And I need to write down the value that we cannot use for x. So I want 3 times x plus 1 not to be 0, because I do not want 0 in the denominator. We can divide both sides by 3. 0 divided by 3 is just 0. So we have that x plus 1 cannot be 0. Subtract 1 from both sides, and we get that x cannot be negative 1. So here, I'm going to write x cannot be negative 1. Notice that f composed with g of x and g composed with f of x are not the same. Composition is not commutative. Okay. Please pause the video and work this problem out in your notes. There are going to be several problems, and I want you to upload those problems at the end of the video all at one time. So go ahead and work out letting f of x be 4x minus 1 and g of x being 3 over x minus 2, and find both f composed with g of x and g composed with f of x. Okay, great. One-to-one functions in the horizontal line test. A function is one-to-one by definition if whenever we have two elements in the range, f of a and f of b, if they are the same, then these input values have to be also the same. Only a function can be one-to-one, so that's very important. And let's look at what this says. So we've got, let's see, here we go. First, let's stick a y on x. So say we have this function. So let's call this f of x. And notice that this definitely does pass the vertical line test. That was the test for functions. It definitely is a function. But let's notice that if I let this value be b and this x, so these two are x values, and I'm going to trace up, and notice that they have the same y. So here, f of b equals f of a. They have the same y value, but b is not the same as a. The x's that went to these y's are different. So this function f is not 1 to 1. One way that you can tell by looking at the graph of a function whether or not it is 1 to 1 is by using the horizontal line test. And do you see why this works? We're looking for places where two y's are the same, but they're hit from different x's. So we want to see, can a horizontal line cross the graph of this thing more than once? Here it's crossing only once, we're crossing actually 3 times. We're crossing 3 times, so this is definitely not 1 to 1. In fact, here's another place. We could call this C and this D. And we can see that f of C is equal to f of D, but C is not D. The x's are different. The numbers that we're plugging in are different, even though they're giving the same y. So this function is definitely not 1 to 1. What does a function look like that is 1 to 1 then? Well, let's look at something a little more interesting. How about this same function almost stretched out? So let's call this g of x. And we need a y and x. Now the first thing to do to see whether or not g of x is 1 to 1 is to see whether or not it passes the vertical line test. Whether or not g is really a function. But I noticed that a vertical line crosses this graph only once. Now I want to do the horizontal line test and see how many times a horizontal line crosses this graph. Does it ever cross more than once? And I can see here it only crosses once. So this function g of x is 1 to 1. I had to show that g was a function first. Okay, great. So let's determine whether this function, g of x, equals 5x minus 4 is 1 to 1. And then we're going to graph g. So we've got g of x is 5x minus 4. That means that g of a is 5a minus 4. And g of b would be just 5b minus 4. And we're going to start by setting g of a equal to g of b. Our goal is to try to get a by itself on one side. So the goal to get a by itself on one side of the equal. So, okay, so let's see. We said that g of a was 5a minus 4. and that g of b was 5b minus 4. And I want to get a by itself, which means first I want to add or subtract any constant. So I'm going to add 4 to both sides. And look what a happy thing that is. We're actually getting rid of the constants on both sides. We get 5a is equal to 5b. Now again, I'm trying to get a. I'm trying to solve for a. So I'm going to divide by 5 on both sides. And happily, that gets rid of the numbers in front of the variable on both sides. And we get a is equal to b. So therefore, these are 3 dots. Therefore, g of x equals 5x minus 4 is a 1-to-1 function. To graph g, I'm going to recall that lines in the form of functions are written as mx plus b. So let's see, here's some room. I've got any line is m times x plus b, where m is the slope of the line, and 0 comma b is the y-intercept. That means for our line, where we have g of x equals 5x minus 4, we have 0 comma negative 4 is the y-intercept. And the slope is 5. Well, that's not exactly a fraction. I always think of a slope as rise over run. Let's write this 5 as 5 over 1. Rise over run. That means I'm going to start at the y-intercept, 0 comma negative 4. I'm going to go up 5 from there and to the right 1. And now that will give us our line. So I'm going to start at the y-intercept, 0, negative 4, go up 5, 1, 2, 3, 4, 5, and over 1. And this is the graph of g of x equals 5x minus 4. And notice that this graph does indeed pass the vertical line test. It really is a function. And it passes the horizontal line test. It really is 1-to-1. Swell. Please pause the video and do this next problem. Determine whether f of x equals 3x plus 2 is a 1-to-1 function, then graph f. So determine whether f of x is equal to 3x plus 2 is a 1-to-1 function, and then graph f. Okay, great. Inverse functions and a test for inverses. When a function is 1-to-1, then there's another function which has this weird exponent, this negative 1 exponent, and we read this f inverse of x. So this is read f inverse. That negative 1 exponent is read inverse, and then the parentheses is of x. F inverse of x undoes whatever f does, and vice versa. when two functions are inverses, the composition both ways equals x. Whatever is plugged in is what comes out when f and g are inverses. Sometimes a function is an important function, but it is not naturally one-to-one. But we need to use it, we need to make it look one-to-one. And let me show you an example. What if we had the absolute value? Can you see that absolute value is a function? Vertical lines cross only once, but it is not one-to-one. Horizontal lines cross twice. To force absolute value function to be one-to-one, we restrict the domain. So the domain restriction that makes sense here is to force x only to be positive or zero. Then the graph is just this right arm. Without the left arm, the graph really is one-to-one. So a domain restriction is something that we impose on a graph we want to use when that graph is not naturally one-to-one. All right, let's determine whether or not f and g are inverse functions by finding f composed with g of x and g composed with f of x. All right, every single time that I've done this recording, I've done it backward, that same way. I don't know why. Okay, so here we've got g of x is 5x minus 4. So I've got g composed with f of x equals g of f of x, which is g of, let's see, f is x minus 4 over 5. And now let's apply g. G is 5x minus 4. 5x minus 4. And we're going to plug x minus 4 over 5 in for the x. Now let's see if f and g are opposites, if they undo each other. From the get-go, I said I've got a 5 in the numerator and a 5 in the denominator. So that's really nice. Now we've got x minus 4 minus 4. Oh, those 4's are both negative. We get x minus 8. That is not x. Let's look at and see what happens if we're looking at the other direction. We have f of g of x. That's f of g of x. Plug g of x in. 5x minus 4. And write down the formula for f. X minus 4 over 5. 5x minus 4. Now let's see if they undo each other. And I notice right away, since these 4's are both negative, the numerator is going to become 5x minus 8. The denominator is going to stay 5. And this is not going to simplify to x. Let's notice something. Let's notice that if we change either one of these very slightly if we let f of x be x plus 4 over 5 and leave g of x as 5x minus 4, then they do indeed undo each other. We have f composed with g of x is f of g of x, f of 5x minus 4, which is x plus 4 all divided by 5. We're going to plug g in here, 5x minus 4. Now notice what happens in the numerator. We have a negative 4 and a positive 4, so they cancel each other. Now we just have 5x in the numerator and 5 in the denominator. The 5's cancel each other, and we're left with x. Let's see if it works the other way as well. We have g composed with f of x, that's g of f of x, which is g of x plus 4 over 5. And the formula for g is 5x minus 4, 5x minus 4, and I'm going to put f of x in for x, x plus 4 over 5, and I'm going to make that 5 look like a fraction so that I can more easily simplify. Notice that I've got a 5 over 1 in the numerator and a 5 in the denominator, so they cancel, they undo each other. Now I've got x plus 4 minus 4, they undo each other, and we're left with x. So these functions, as they were given, were almost inverse functions. Please pause the video and work out this problem in your notes. Let f of x be 3x minus 2 and g of x be x plus 2 over 3, and determine whether f and g are inverse functions. By finding g composed with f of x and f composed with g of x. There's a theorem called the symmetry of inverse functions theorem that is really powerful and amazing. And it says, focus, it says that if I have the graph of a function, and say a typical point on this graph is a comma b, then any point on the inverse function will have to have the point b comma a. A function and its inverse have the same points, just flipped. A function and its inverse are symmetric with respect to this line y equals x. That's the line that cuts the first quadrant and the third quadrant in half. So to find the inverse of a function graphically, we're going to see if we need to restrict the domain of f so that it is a one-to-one function, then switch the order of every point in f and connect the dots, see what we get. This new graph will be f inverse of x. So the first example is to look at f of x equals x squared. When we're asking the question about whether or not y equals x squared is one-to-one, it's like asking whether x equals y squared is a function at all. These are the same questions. Asking whether y equals x squared is 1 to 1 is the same as asking whether x equals y squared is a function. And we can see x equals y squared does not pass the vertical line test. And also, y equals x squared does not pass the horizontal line test. So, does not pass the horizontal line test. So, f of x is not 1 to 1. And here we would say x equals y squared does not pass the vertical line test. So this graph is not a function. Well, we can't just not use f of x equals x squared. It's a really useful function. So what we need to do is restrict its domain. And the natural restriction is to let x be greater than or equal to 0, so that we only have this right arm and that means if we flip it, we'll only have this upper arm, the lower arm will be gone, and we will indeed have a function. So let's take this single arm of the function f of x equals x squared, where x has to be greater than or equal to 0. Let's find some points on here and graph the inverse of f of x. I see several nice points. Let's see, we've got 2, 4, 1, 1, and 0, 0. Well, the frustrating thing about 0, 0 and 1, 1 is that they're both on this line, y equals x, which means if I flip the order, I'm still on that line. So let's do it carefully. I know that I'm still going to have the point 0, 0, and also the point 1, 1 on my inverse of f of x. But this point 2, 4, when I flip that, it becomes 4, 2. Let's see, 4, 2. And now, also I see that between 0 and 1, the graph of f of x is below the line y equals x. That means that f inverse is going to be above, and here is the graph of f inverse of x. So even if I didn't know what that function was, I can draw its inverse and I can use it. We do, though, know that here f inverse is the square root of x. And that makes sense because square root and square undo each other. So the domain restriction is really important in allowing that to happen. want you to answer these questions in your notes for the function cube root of x. Is y equals the cube root of x 1 to 1? So here's the graph of the cube root of x, and here's the line y equals x. Does y equals the cube root of x pass the vertical line test? Does it pass the horizontal line test? And that's the same as asking, does x equal the cube root of y pass the vertical line test? Horizontal line test for y is the same as the vertical line test for x. Now use the sketch of the cube root of x. So this is f of x equals the cube root of x, to draw a sketch of its inverse function. And we can kind of do this together. I notice I have 3 points, but they're all on that line y equals x. In other words, if I switch the order, I get the same points. But that's okay because I can see what happens between these points. So let's go ahead and sketch. I can see that below x equals -1, the graph of f is above this line, y equals x. So I'm going to start below. In between I go above. In between I go below. I'm going to hit up. So f inverse of x. So say I didn't know anything about what the inverse of cube root was, I can at least draw its graph. And we do know what the inverse of cube root is. It's cubing. But the idea is that we can start with a graph, switch the order of all of the coordinates, and get an idea of what the inverse looks like, even when we don't really know its name. To find the inverse of a function algebraically, you replace f of x with y, switch the variables x and y, solve the new equation for y in terms of x, replace y with f inverse of x. Again, read this f inverse of x, f inverse of x. You read that -1 as inverse, and then check the result by finding f inverse of x, f inverse composed with f of x, and f composed with f inverse of x. So let's find the inverse for the function f of x equals 3x minus 4 using those steps. So step 1 was to change f of x to y. So f of x becomes y. Step 2, we're going to switch x and y. So we'll have x is equal to 3y minus 4. We're going to now solve this new equation for y. So let's see, I've got x equals 3y minus 4. To get y by itself, I need to add 4 to both sides. So I've got x plus 4 equals 3 times y. Finally, to get y alone, I need to divide both sides by 3. And I get y is equal to x plus 4 over 3. Step 4 is to replace y with f inverse. F inverse of x equals y. And then step 5 is checking. So let's find f composed with f inverse of x. So let's see. I have to rewrite this so I know what it means. F of f inverse of x. So it's f of, the formula for f inverse was x plus 4 over 3. And the formula for f was 3x minus 4. Notice that the first thing that we can do is divide out these 3's. 3 divided by 3, those cancel, they undo each other. Now we're left with x plus 4 minus 4. The 4's undo each other, and we're left with x, which is what we want. Let's try the other direction. Let's find f inverse composed with f of x. Well, that's f inverse of f of x. That's f inverse of, the formula for f of x was 3x minus 4. And the formula for f inverse was x plus 4 over 3. X plus 4 over 3. And we're going to plug in 3x minus 4 instead of x. And what happens immediately? In the numerator, we have 3x minus 4 plus 4. Now we just have 3x over 3. The 3's cancel or divide each other out, and we're left with x. So the two functions undo each other differently. When we found f composed with f inverse, we divided first by 3, and then the 4's we're getting rid of. When we found f inverse composed with f of x, the first thing we did was cancel out the 4's, and then we divided by 3. Oh, and I wanted to graph these because it's really cool to see the two functions. So to graph 3x minus 4, I know that 0, negative 4 is the y-intercept of f of x, and that the slope is 3 over 1, a rise of 3 and a run to the right of 1. So let's start with 0, negative 4, go up 3, 1, 2, 3, over 1. And I'm going to do it one more time so I get a better graph. Up 1, 2, 3, over 1. There's my graph of f of x. To graph f inverse, I want to do one step to my function for f inverse. I want to write this denominator of 3 separately. So I'm going to write x over 3 plus 4 over 3. And that x over 3, that's the same as 1/3 times x plus 4/3. So our y-intercept here is 0, 4/3, and the slope is 1 over 3. Up 1 to the right 3. So let's start at the point 0, 4/3. And go up 1 and to the right 3. And I'm going to do it one more time. So I'm going to go down 1 and to the left 3. 1, 2, 3. Just to get a little bit of a better line. This is the graph of f inverse of x. Notice that they cross on the line y equals x, and that if we folded this whole graph along that line y equals x, the two graphs f of x and f inverse of x would match. Well, I want you all to do all those same things with the function f of x equals 1 plus 2x. So I want you to find f inverse, show that f composed with f inverse and f inverse composed with f both equal x, and graph both functions. So please pause the graph and go ahead and do this in your notes. All right. Well, thanks for hanging around, and let's hope this works. Have a great day.